Okay, good morning, guys. Today we're going to do 5.1b, which is still Riemann sums. However, we're going to learn a new way to type them into our calculator. It's going to get even easier and easier, hopefully. It's really an important foundational look at what we're doing that, and towards the end here, you're going to see, the end of this video, you're going to see how these Riemann sums are going to be able to look on the AP exam, and then they're going to ask you questions about it, and we're going to build into that. But recall, the total area is the sum of the heights, and the heights, okay, those are my rectangles up here, okay? And in order to find the area of a rectangle, we're taking height times width, where the sum of the heights, remember, is the sum of the f of c sub k values, and the widths, okay, were my delta x values. That always gave me my width and my height, where c sub k is some x value in the kth interval. And if you remember, we used the left endpoint, the right endpoint, and the midpoint for three different ones. Well, as we are typing these into the TI-NSpire, the method in which you're going to learn today, is please understand that as this all comes through into a very ginormous looking function like this, into summation notation, okay, when we're doing this with our TI-NSpire, we are always going to be using the right endpoint, okay? So for the TI-NSpire and algebraic reasons for the notation, we will only be using the right endpoints. And as we continue and we get more and more rectangles, as n approaches infinity, the number of rectangles approaches an infinite number of rectangles, it doesn't matter if it's the right endpoint, the left endpoint, or the midpoint, or any point within your rectangle. As n goes to infinity, it just straight up does not affect the area at all, period. Okay? And then remember here, our area is the sum of all of my widths times the height, or the sum of the widths and the heights in there. Okay, so remember, k is going to equal 1, then 2, then 3, then 4, then all the way down to the nth rectangle, where k is just our counter. And we're going to learn how to really be taking the sum of all our widths and heights and put it into what we call summation notation. Which is just that E thingy, as everybody like to call it in Algebra 2, that E thingy, which is the capital Greek letter sigma. Okay, so as we're moving along here, we're not going to write it out the same way we did the last 2 days, because you would get really ticked off with me if I had you do that. So what we're going to do is we have f of x here, and we are going to estimate the area on the interval from 1 to 3, and we're going to use 10 rectangles this time. So this is why we're going to start writing it different, because we're going to go from 10 rectangles to 50 rectangles to 100 rectangles to 1,000 rectangles to an infinite number of rectangles, and it just gets really cumbersome to write. So that's why we're going to go into our sigma notation. Now remember, there's 3 important values that we need to know. Okay, we have our delta x sub k, that is the width of our rectangle. We have our c sub k, that is the x value within our subinterval in which we are going to plug into our function to get the height of our rectangle. Okay, remember this is my height right here, and this is my width right here. Okay, and those are the 3 special things we need to know. Now, as I'm going here, well, I think everybody can look at this and say, hey, up here, I know this is a parabola. It's going to hit the y-axis at 9, and it's going to be concave down. So it's going to kind of come like this. My x-intercept, hopefully we can look at this real easy and say, hey, it's going to hit the x-axis at 3. And what we're doing is we're splitting 1, 2, 3. We are going to be splitting this little bugger into 10 rectangles. Oh my God, what's the width of each rectangle? Well, remember as we came along here, and I'm just going to dictate it as delta x, the first thing we need to find is we need to find our delta x. Now remember, delta x is always going to be b minus a divided by n, where there's my a value, there's my b value, there's my n value. A is the first x value in the interval, b is the last one, and n is the number of rectangles. So this is going to give me 3 minus 1 over 10, or 2 over 10, or that's going to equal 0.2. That's my delta x sub k. That's the width of all of my intervals, okay? Which means I need 10 rectangles in here, and we don't have to even draw them all out, but that means each one of these is going to be 0.2 wide, 2, 3, 4, I'm going to have that 5 one, we're going to have 6, we're going to have 7, we're going to have 8, and we're going to have 9 and 10 in there. So we need to know what our delta x is. Well, the next important thing we need here is we need to know what the heck is c sub k. Like I said before, c sub k is going to be the x value, okay, that we will use in our interval to find our height. And for the purpose of today, everyone, we are always going to use the right endpoint, which means we will be finding the right RAM each time. In this case, it would be the right RAM of 10. But I'm not going to have you write it out the same way, okay? So what we need to think about here is if we're using the right endpoint each time, okay, I need to figure out, because there's 10 rectangles in here, and I go from 1 to 3, well, bottom line, if I'm using the right endpoint, I will be finding this rectangle right here, correct? Which means my first c sub k value is going to be c sub 1, and that's going to be 1.2. My second one, c sub 2, hopefully we can see that's going to be 1.4. And c sub 3, it's going to be 1.6, because I'm just going through all of those. And then it's going to go all the way down to my c sub 10, and my last endpoint is going to be what? Well, c sub 10 is going to be 3. Well, I really want to be able to symbolically represent this so I can type it into my calculator into a very nice function, because we're going to be writing a summation notation out of these. And let's just think about all of these here. And I'm going to kind of change colors. Where did this c sub 1 come from? Well, it really kind of came from 1 plus 0.2 times, see, I just gave up the whole thing here. I just gave it up. But I'm using my width every time. And this one's going to be 1 plus 0.2, but it's 2 0.2s down the road. So I would multiply that one to get my c sub 2 would be here. My c sub 3 is going to be 1 plus my jump, or my delta x of 0.2, but now I need 3 jumps to get in the third triangle. And then I'm going to come all the way down here, and I'm going to take 1 plus my delta x times 10 jumps to get down there. And like I said, this first one is 1. Well, what do we want to call that number in the parentheses? Because we want to, what we're doing is our goal is to be able to write our function in summation notation, so we can type this into the CAS and have the CAS give us the area. So we're going to kind of be looking here. Well, if I put all of these together, okay, I can get a little crafty, and I can think of, what is my c sub k value going to be? Well, that c sub k value is going to be 1 plus my 0.2. And what do I want to call these? 1, 2. Remember, that's like the number of rectangle. That's the rectangle number we were on. And what did we call that? We called that k. Okay? So these delta C sub, or not delta, these C sub k values are actually pretty easy to come up with when I think of it as a right endpoint each time, because C sub k is always going to be pulled. Well, where did that 1 come from? Well, if I think about it, oh, that 1, that was my A value, plus, where did 0.2 come from? Well, 0.2 was my delta x value, and then I took that delta x value times the k I'm on there, and it gives me a little formula that always gives me the C sub k, or the height, with a right ram. Okay, it's important to know this is always going to be a right ram for us here. So as we continue on, okay, so now we have our C sub k values. So the third thing we're going to want to do is we need to come down here for number 3. Well, now we want to know, what are our heights? And our heights, remember, those are our f of C sub k values. Well, what are my heights going to be? Well, my heights are going to be f of 1.2, f of 1.4, f of 1.6, all the way down to f of 3, right? And this is what we want to get away from. What we're doing is we're getting away from, because you would be kind of ticked, and I'm going to write this out. Let's say I wanted to find, the area is going to be my delta x times the sum of all these heights. F of 1.6 plus f of 1.8 plus f of 2 plus f of 2.2, f of 2.4 plus f of 2.6 plus f of 2.8 plus f of 3. And as I did that, if I kept doing that, okay, I know you guys weren't happy. Yesterday I was okay with it because there was only 5 heights that we listed out. But as n goes from 10, and then we're going to do it again with 50, and then 100, okay, this gets pretty cumbersome to write. That's why we're not going to do it that way, and we're going to learn a new way to type it into our CAS calculator today. So I'm going to get rid of that. And as we are moving along here, number 4, okay, the area, I know in the end, the area is approximately equal to 0.2 times f of 1.2 plus 0.2 times f of 1.4. I don't need those parentheses in there, but it doesn't matter. Plus, plus, all the way down to my 0.2 times f of 3. Okay? And that gives me my area. Now, what we want to do is we want to figure out how can we fit this, okay, we want to fit that into our summation notation, where our k value starts at our first rectangle, it goes to our last rectangle of f of c sub k times my delta x sub k. That's calculus notation for this. Well, let's think about this now. What do we have? Well, here in this example, here for this particular example, we know f of x is 9 minus x squared, right? We know n equals 10. We also know delta x equals 0.2. Hold on. Okay? And I also know my c sub k values are going to be 1 plus 0.2 times k. All right? Now, what we're going to do is we're going to put all of this stuff together to get this into a sigma notation, because our CAS calculator is going to deal with this sigma notation for us, okay? And that is going to take us to our sum. K always is going to be beginning at 1. Now, note, n is 10, okay? What is my f of, what is my f of c sub k? Well, f of c sub k, this is going to give me f of 1 plus 0.2 k. that represents all my heights. Remember, k is going to start at 1, and then it's going to go to 2, then it's going to go to 3, all the way to 10, and then that's times my delta x is going to be 0.2. And what we want to do is we want to figure out how to get that into our calculator. Okay, there's two ways to get this into our calculator now. Okay, and when we get this into our calculator, and just, you know, not to beat the dead horse here, but when I plug in k equals 1, what that's going to do, that's going to give me f of 1.2 times 0.2 plus then k equals 2. Well, 0.2 times 2, that's going to give me f of 1.4 times 0.2 plus all the way through, dot, 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 all the way through until I put my 10 in there. That's going to give me my f of, well, 0.2 times 10 is 2 plus 1 is 3 times 0.2. Okay, and that is going to, when I add all those up, that's going to give me the area of my approximated curve underneath here. Now, of course, it's using a right ram in this case, so we are going to be an underestimate here because I can see all these rectangles are going to be underneath. Okay, and when we're doing this, okay, in our calculator in this fashion, we will always be using the right endpoint, because as we continue on in this class and n goes to infinity, it really is not going to matter anymore. Okay, so there's two ways to put this into your calculator, into the TI-NSpire. Okay, so what I'm going to do is son of a biscuit. I'm going to come down here. I'm going to say there's two ways, both of which you really want to know, okay? And there's two ways to go into the calculator. The first way, the easiest way, the way I recommend you put it into the calculator, is we are going to define our function. We're going to define f of x as, 9 minus x squared in this problem. And when we define it, then we are going to type into our calculator k equals 1 to 10, because that's it, of f of, because f is going to be defined, 0.2k times 0.2. This is going to give me my area, okay? So what we're going to do is we're going to come here to the calculator. First thing I need to do is I need to menu, actions, define, and I need to define f of x to equal 9 minus x squared. Okay, and it's done. And if you don't trust yourself, you can plug a couple values in there to make sure they'd be right on your graph. Well, from here, there's two ways to get at the sum. Okay, it's either that guy right here, which isn't working in my calculator, it gives me the big E summation. Okay, if I go back now, I can hit my little template right there next to the book. Whoa, escape. I can hit that little template right next to the book, and it's the one that's highlighted right there. Or if you didn't want to use that, what you can do is you can say menu, you can go to calculus number 4, and this is going to be a sum number 5. And all we're going to do is we've let that lower limit down there, we called that k, and then I'm going to hit tab, and k is going to go from 1. Then I'm going to hit tab, and it takes me right to the top. My upper limit is 10, then I'm going to hit tab. Now in here, the reason I defined it is because I want to say what is f of 1 plus 0.2 times my k value. And if your k is a bold-faced letter in there, okay, we have an issue. Then you have something stored in k, which we don't want. Then I still have to toggle. I have to arrow outside of that function form and say we're going to take u times 0.2, which is the width. And then we are going to simply hit enter, okay? And I get 8.52 is my approximation, hopefully there. So I'm going to come down here, And I'm going to say, oh, this equals 8.52 is my area, okay? This doesn't tell me, okay, one thing to note, this is the area approximated under that curve using 10 rectangles. Now, this notation right here, this does not tell me what f of x is, okay? So the way the AP board is going to give you this summation notation on problems is they're going to look at it just like this. They're going to say the sum from k equals 1 to 10, and you can type them in like this too, but they're more cumbersome to do. And then because f of x equals 9 minus x squared, they're basically going to say 9 minus x squared, and I'm going to leave myself a little room here, because that's my f of c sub k, and then that's going to get multiplied times my 0.2. Well, where they make the difference here is because I'm plugging in, I need to know what my c sub k is, so they're going to get rid of that x, because remember, we're plugging in for k, so that x is going to be replaced with my c sub k right here, which is going to be 1 plus 0.2k, and then that's going to be squared. So now, okay, by the time you hit to the AP, they're going to say, oh, this summation represents what? And you're going to be able to look at this and you're going to say, f of x, which equals 9 minus x squared, and this is the area for the interval from 1 to 3 with 10 rectangles, okay? And you're not there yet, and that's fine. You're going to be able to translate this into 9 minus x squared dx from 1 to 3, and we're going to be able to get there, but we're not there yet. But that's where the AP board wants you to be able to take that notation. This is the AP notation here to get into this, and we will get there. We're not going to quite get there today yet or tomorrow, but that's the ultimate goal where we're going, okay? Just so we know. And I can also type this into my calculator in the same way if I wanted to, without defining it, because I could say menu, calculus, sum, and I could say my limit from k from 1 to 10, and then I'm going to hit tab, and then I have to say 9 minus parenthesis 1 plus 0.2 times k, close parenthesis, then I'm going to square that, and then I'm going to have to get on the outside of that little rascal and say times 0.2, and that should give me the exact same thing. But when I'm in this notation right here, this is the AP notation, you will be able to look at this. You will be able to say the function is 9 minus x squared. It's the area from the interval from 1 to 3 underneath the curve, okay? And that's where we're getting. So that's where we're heading, and I'm going to minimize that down, and we can see that this same thing still equals my 8.52, okay? So now what we're going to do, remember, this is how the AP board is going to do this, and what we're going to do is take that same exact function, and now we're going to say there's going to be 50 rectangles in there. What is my area approximation? And hopefully you know, okay, if I'm slamming 50 rectangles in that interval, it better be a better approximation than it is with 10, right? So that's where we're going to go, and that's what we're going to be doing, and we're going to fill out these 3 critical pieces of information so we can type it into our calculator easily. Okay, so if we want to change this, where n is 50 rectangles now, you're welcome. I'm not going to make you write all that out. I know nobody would do it anyway, so to Delta x, remember that's always b minus a divided by n. So that's going to be 3 minus 1 over 50, which is 2 over 50, which is really 4 over 100, which is 0.04 is my delta x, okay? Now, c sub k, remember we're always going to be using the right endpoints, and c sub k is always going to be a plus delta x times k. So my c sub k is actually going to equal 1 plus 0.04 times k. That's my c sub k, which means my area function is going to be approximated by the sum from k equals 1 to 50 this time of f of c sub k is 1 plus 0.04 times k times 0.04, okay? Just know that's the easy way to type it into the TI-NSpire. Calculus version, I'm not even going to say approximately because it's not approximately equal to. The calc version is going to look like the sum from k equals 1 to 50 of 9 minus my c sub k in for all my x's, 1 plus 0.04 k, it's going to get squared, times my delta x of 0.04, okay? And that would be my algebraic or my calculus notation from it, okay? It's just easier to type into the TI-NSpire this way, in my opinion. So then all we're going to do is we're going to come back and we're going to grab our calculator, and all I really have to do is come up and grab one of these guys and scroll over here to the top and change that, whoa, to 50. And I also notice I had to change my delta x too. My delta x, oh, son of a biscuit. So I'm going to hit pause and enter it because this thing's being stupid. Okay, so I'm going back to the easy one, not the one I grabbed before. I'm going to type in the function form because I already have f of x defined in there. And f of x is still my 9 minus x squared. Only thing that's different is my c sub k changed and my delta x changed. That's the only thing that's different. So I'm going to hit enter, and that's going to give me my area with 50 rectangles, and that should be 0.9 or 9.173. Okay, so this equals approximately equal to 9.173 rounded to 3 decimal places. Then guess what we're going to do? Then we're going to come here, we're going to do the same exact problem, except with 100 rectangles. Well, that's 3 minus 1 over 100, which is 2 over 100, which should give me my delta x of 0.02 is my delta x, okay? Well, c sub k, remember that's a plus delta x times k. So that's going to give me 1 plus 0.02 k. So my area, my sigma that I'm actually going to plug in is k equals 1 now to 100 of f of 1 plus 0.02 k times 0.02. Okay? And just to say, the calc version is going to be the sum from k equals 1 to 100 of 9 minus 1 plus 0.02 k squared times 0.02. And this is the really important one in the end, okay? You're just going to be looking, and you're going to be looking at that, and you're going to be saying in the end, oh, okay, well, I know this is going to be the integral. I know I'm going to look at this, and I can say, oh, f of x, it's 9 minus x squared. I can see it. I know the interval in which I'm talking about. I can see my a is 1. I can see my width of my total overall interval is 2. So if I add 2 to 1, I get to an endpoint of 3. And I can find all that from there. We're going to be there in a minute. Well, it's going to take you a little bit. Then all you come back, grab your calculator, toggle up, grab that one, and hopefully, no, I don't want to toggle up. I'm going to try to come over here, and I'm going to say tab, delete, delete. I'm going to put 100 up there now. Then I'm going to say, I didn't want to go there. Now I got to come over here, and I got to toggle. Now it's 0.02. This is my width change, 0.02. This is going to approximate now with 100 rectangles. And 9.253 I get. Okay? So this is approximately equal to 9.253. Then guess what we're going to do? You guessed it. We're going to do it with 1,000 rectangles. Same function, same interval. Now, what we should be noticing is our estimate's getting better and better and better. 3 minus 1 over 1,000. That's 2 over 1,000. That gives me what? 0.002, right? This is 0.002. Well, what is my C sub k? Your C sub k, because we're always using right endpoints, it's always going to be a plus delta x times k, or it's going to be 1 plus 0.002k. And to type this in, we want to see it in sigma notation, where k is going to start at 1 and it's going to go to 1,000. Okay, of f of 1 plus 0.002k times 0.002. This is going to give me my area. If I can sound like a broken record. The calc version, how you'll see it on the AP calculus test. And you can type them all in this way. K equals 1 to 1,000 of 9 minus 1 plus 0.002 squared. There's all my f of c sub k's. When k goes in there for 1, I get my functional value for the height times 0.002. There's my delta x. And that's what my calculus version is going to get. And then I'm going to come back to my calculator, and I'm going to come up, and I'm going to say enter. I'm just going to come back up. And I'm going to change this as they come across. I think I got to add a 0 in that one. And I got to add a 0 in that one. And I got to come over here, and I got to add a 0 for 1,000. And I believe that should get there, and I get 9.325. Okay, 9.325, 9.325, 9.325. And what I see is they're getting better and better and better as I go. Okay, so what happens as n gets big? Kind of sounds like a limit to me. Well, it is a limit. Okay, so what are we doing? N is going to infinity. I don't know how many there are. There's an infinite number. Well, this changes all my notation, guys. It changes everything a little bit. Delta x, it's still b minus a over n. Okay, remember, I'm still using the same function, 9 minus x squared from 1 to 3. So as I come in here and I put it, well, that's going to equal 3 minus 1 over n, because I don't know what n is. So 2 over n, that's my delta x. N is infinity. Well, n is going to go to infinity, but you don't really get to infinity. That's why I'm leaving it a variable. Okay? C sub k. Again, a plus delta x times k. Well, what is that going to give me? That gives me a plus delta x times k. There is my c sub k. And what do I get? I got to plug it in for my summation. Well, now k is going to go from 1 to n because there's going to be n of them in there. And the way we're plugging it in, 1 plus 2 over n times k times 2 over n. Well, the calculus formula of this looks a little bit different. This is the one that's going to be super imperative that you understand down the road. The sum is going to be from n equals 1, or excuse me, k equals 1, sorry. Oof. K equals 1 to n, where n is anything. And this is going to give me 9 minus the product, or the quantity 1 plus 2 over n k, and that's going to get squared, times my width is 2 over n, okay? This is going to be what you're going to look at. And it's going to say the following sum represents the area of what function between which two limits, okay? And what's going to happen is this is what we're really going to understand. We're going to understand here that this is going to be the integral. I can see my f of x function. I can see my width, dx, okay? And I know, how do I know I'm going from 1 to 3? Well, I know I'm going from 1 to 3 because that is my a value, isn't it? And my a value is always right there. So that's going to be my lower limit. And this is the width. This is the overall width of my interval. So if I change that and I put that from 1 to 3, okay, because if I add 2 to 1, I get 3. Well, this could change numerous different ways, just so we know. If this all changed, okay, for instance, my interval can change. It can be anywhere. Let's say I'm going from 4, and the 2 is still up there. Well, now a equals 4. My overall width is still 2, so that's going to be 4 to 6. And I can see it, and I can see my function in there, okay? That's where we're going with it. You can see f of x. You can see the interval from a to b. And this is going to extract the actual area. But what do we get when we type this into our calculator now? Okay, if you took yourself out of exact mode when I was here because you're sick of all these decimals, you might want to put yourself back in exact mode, because now we're saying menu calculus is going to be a sum. We're saying k from 1. Now we're going to n. Where's my n? Here's my n. Of, I still have the same function, f of, but I'm going to type it in as 1 plus that fancy little fraction of 2 over n, and then that's going to be times by k, and I got to toggle outside of that and say times this fancy fraction of 2 over n, because that's my width. What happens is I get a whole function. Oh, see, I didn't change mine. I'm not in exact mode. So what I'm going to do is I'm going to come back here and I'm going to change my settings, number 5, my document settings, number 2, and I want to go to my calculation mode. I want to be under exact, and I'm going to make that my default and say OK. And then I'm going to come back to my current, and I'm just going to come back up here because this right here is a pretty ugly one to read. But if I'm in exact mode and I bring that down and I hit exact, oh, well, look at there. I get a rational function. Okay? So what I end up getting out of here is, and when I rewrite this, I'm just going to distribute my 4. Okay? So when I get up here, this sum here equals, it's going to end up equaling 28n squared minus 24n minus 4 over 3n squared. Well, what is n? Okay, well, n is the number of rectangles. But watch this. This is even more cool what the CAS does. If I came up here and I grabbed that and I came over here and I said, I think I say the such that, which is control equal, and I use the such that bar, such that n equals 10. Okay, this would be my 10 rectangle approximation, and I hit enter. Ooh, well, now I got to come up here because I just changed from exact mode, and I'm going to say here Control Enter. Oh, 8.52. And let's say I came up and I grabbed that again. And I said, oh, let's let n equal 100, or no, 50 it was next, right? Delete, delete, delete gives me 50. And then if I say Control Enter, 9.173. Boy, that one looks familiar too for my n equals 50. If I came up here and I grabbed here and I ended up making n, whoa, be 100. Okay? When n was 100, we got 9.253. Well, what do we get? 9.253. So when I let n in the top, when I let my upper limit become n, what happens is it's writing me a function that allows me to come back, and there's my 1,000, 9.325, excuse me. What it does is it gives me a function that allows me to put the number of rectangles anywhere in here, and it'll approximate. And I could do it with 35 rectangles if I want, then n would be 35, and it's going to give me that approximation. But like we said before, looks like a limit. So if I come back here and I take the limit of this thing as x approaches infinity, well, I can go through here. If I really want to do it hard, I can say, oh, I plug infinity. I get infinity over infinity and apply L'Hopital's rule. But the actual easiest way to do this is say, hey, this is a rational function. It's going to be the big dog over the big dog. This is going to equal 28 thirds. Well, what is 28 thirds? 28 thirds is actually 9 1/3, or it's actually 9.333 repeating, or 9.3 repeating. And what is that? That is the exact area under the curve. It's the exact area, not approximate anymore, as I go to infinity. So what does this mean? Well, what this means is it's kind of wild and wonky, but if I take that summation that I have here, I used to do this and kids hated me for it, from k equals 1 to n, I used to make them do these, of my 9 minus 2 over n times k times 2 over n. As soon as we come back here and we take the limit as n approaches infinity of that sum, this gives me 9.333 exact area, or 9 1/3. It gives me the exact area under the curve. Okay? And I can type that, and my calculator will do it for me too. I could even come back here, and I'm going to say menu, calculus. We're going to do a limit as n, okay, as n goes to, infinity is down here by your pi key, and I'm going to put an infinity in there, of, and now I got to hit a tab, and what I want to do is I want to do the limit, and now I want to find that sum that I did before, and it doesn't matter which one I do. Okay, where are you, you dirty dog? Come on. I want to do the limit of that sum right there. As soon as I plug that guy in there, and then I hit enter, well, 28 thirds. What is 28 thirds? And if I forgot to hit my approximate, oh, it's 9.33 repeating, and it gives me the exact area. Do not worry about any homework tonight, guys. Tomorrow's video is going to kind of be short and sweet. All I'm going to do is I'm going to go through the last 3 examples on this page, and the rest of the time will be work time. Hopefully I can keep it to about 15 minutes, and you'll have time to work on 5.1b and finish up anything with 5.1a. So hopefully this is making sense. If it's not, reach out to me, please. And hey, thanks for playing math with me today.